Picture this. You see these brilliant flashes of lightning tearing across the sky. You hear that deep rumble of thunder. So naturally, you look outside, you're expecting a huge downpour, but the ground is completely, totally bone dry. It's a storm with all the sound and fury, but zero rain. Now, this isn't science fiction. This is a real thing called a dry thunderstorm. And today, we're going to figure out how this incredible atmospheric paradox is even possible.
Right? So, lightning with no rain. How does that even work? Well, the key to understanding this is knowing that even though they almost always show up together, lightning and rain are actually created by two totally separate processes high up inside a storm cloud.
Okay, let's dive into this. To really solve the mystery, you have to kind of decouple these two things in your mind. Think of it this way. They might show up to the same party, right? But they got there in different cars. Lightning, that's an electrical event. Rain, that's a physical one. And this really lays it all out. On one side, you've got lightning. It's just a massive electrical spark, a discharge, created by a charge imbalance inside the cloud. And on the other side, there's rain. That's a physical thing, where little water droplets just get too heavy and fall. They can happen at the same time, for sure, but one does not require the other. You can think of a big thundercloud as a giant electrical generator in the sky. Inside these huge cumulonimbus clouds, you've got this wild, chaotic mix of air currents, updrafts and downdrafts, just tossing around tiny bits of ice and supercooled water. Meteorologists call them hydrometeors. And it's all those collisions that kick off the whole process of making lightning. Yeah, it really just boils down to these three simple steps. First, you get the collision. Lighter little ice crystals smash into heavier ice pellets called grample. Second, there's a transfer of charge. These collisions literally strip electrons away. And third, separation. The updrafts carry the lighter, now positively charged crystals way up to the top of the cloud, while the heavier, negatively charged grample sinks to the bottom. And boom, you've turned the cloud into a giant battery, just waiting to discharge. All right, so we figured out how lightning can form all on its own. But here's the thing. In a lot of these dry storms, rain does actually form, which of course leads to the next big question in our investigation. So yeah, if the cloud is making rain, why in the world isn't any of it reaching us down here on the ground? Well, the answer isn't that the rain just disappears into thin air. It's that it has to survive a pretty brutal journey down to the surface. And it's a journey it often doesn't make. And this phenomenon actually has a name. It's called virga. You've probably seen this yourself without even knowing it. You look up and see those wispy trails of rain falling from a cloud that just seem to stop in midair. It's not an optical illusion. That is literally rain vanishing before it ever gets to you. The culprit here is a deep layer of really hot, really dry air sitting between the bottom of the cloud and the ground. And this air acts like a giant thirsty sponge. So as those raindrops start to fall into this layer, the air is so dry and so warm that it causes them to evaporate completely long before they have a chance to hit the pavement. The lightning, it gets a free pass, but the rain, it just doesn't make it. Okay, so virga explains the vanishing rain, but what are the perfect conditions for this to happen in the first place? Well, it turns out there's a pretty specific recipe you need to cook up one of these rainless storms. You're going to find these storms most often in arid and semi-arid places, like the American West. Deserts obviously have that super crucial layer of dry air we talked about. Mountain ranges can force moist air way up high, creating what are called elevated thunderstorms that are totally disconnected from the dry surface below. And sometimes you'll have a cold front pushing into a warm, dry air mass, creating storms where the moisture is way up high while the ground stays totally dry. Now, these dry environments can do something even weirder to the storm's physics. Sometimes the cloud's internal battery, it actually flips its polarity. So instead of having a negative charge at the base, the bottom of the cloud becomes positively charged. And that leads to a much more powerful kind of lightning.
And we're not talking about your average lightning bolts here. This positive lightning is way more powerful, and it can strike super far from the storm itself, seemingly out of a clear blue sky. I mean, these things can travel for tens of kilometers horizontally before they finally strike the ground, catching people completely off guard, miles away from any visible rain.
So, we know how they form, we know the science, but why should we care so much? Well, because when you combine a powerful ignition source, like lightning, with a very dry environment, what you get is a recipe for absolute disaster. This is the #1 reason dry thunderstorms are so feared. A single strike can ignite parched grass, dry brush, or an entire forest.
And without any rain coming down with it to dampen the fuel, a tiny spark can explode into a massive wildfire in just minutes.
I mean, this table just makes the danger crystal clear. A wet storm, it soaks its own potential fuel. A dry storm strikes ground that's already tinder dry. But look at that wind factor. That evaporating rain, the virga, it cools the air it falls through, which creates these dense columns of sinking air. And that can cause these violent downdrafts called microbursts, which act like a giant bellows, fanning the flames and spreading the fire with terrifying speed. So you end up with this perfect storm of wildfire conditions. You've got an ignition source coming from the sky, absolutely no water to put it out, and you have strong, erratic winds generated by the storm itself to push the fire across the landscape. It's just an incredibly dangerous combination. And, this isn't a new fear. For centuries, cultures that have lived in arid lands have recognized this terrifying paradox. In societies that depended on rain for their very survival, a storm that brought only the threat of fire, without the life-giving blessing of water, well, it was seen as a terrible omen, a truly destructive force of nature. And that brings us to today. As global temperatures continue to rise, many regions are just getting hotter and drier. Climate models are suggesting that we might not only see more lightning in general, but also a higher percentage of that lightning happening in these dry conditions. So the question we're left with is a pretty sobering one. Is this atmospheric paradox on its way to becoming a frighteningly common new reality?